Picture peering into the absolute abyss of the universe. But we're not looking through the blurry, pixelated lenses of the past anymore. We're looking with staggering, hyper-realistic clarity. Welcome to this explainer. Today, we're unpacking a genuinely fascinating July 2026 paper that completely redefines how we search for alien life. We're diving into a revolutionary framework built by Lázaro López Paz and DeepSeek AI. So, buckle up, because what we're going to explore today will absolutely change your perspective of the cosmos forever. Staring into this cinematic vastness, we really have to ask ourselves a pretty profound question. Are we searching for life with the wrong tools? See, right now, astrobiology is hitting a massive bottleneck. We have these incredible telescopes, right, like JWST and TESS, but they are literally drowning us in oceans of complex spectroscopic data, climate models, and biochemical signatures. We get this breathtaking view of distant exoplanets, sure, but we are suffocating in the high dimensionality of all these parameters. We just can't pinpoint the living ecosystems hidden inside the noise. Okay, let's dive right into this. Historically, we've leaned on traditional metrics, things like the Earth Similarity Index or the Planetary Habitability Index. The problem? They rely on simple geometric averages, basic linear math. But nature, and certainly the universe, is anything but linear. Using those old indexes is basically like trying to measure a massively complex, multi-dimensional reality with a flat wooden school ruler. It just doesn't work. Enter the new LCPB index. This is a massive leap into high-dimensional, nonlinear quantum algorithms. Section 1. Introducing the LCPB index. So meet the Logarithmus Biologicus Quanticus, or LCPB. This is a fully functional framework that evaluates the probability of a biosphere, and it breaks things down into 4 dynamic components. First up, favorable factors. Think water and temperature. Second, risk factors, like intense UV radiation. Third, and honestly here is the real magic, nonlinear biological synergy. And finally, a Bayesian correction, which basically acts as our reality check. The algorithm takes this massive, tangled web of data and compresses the whole shebang into one incredibly powerful single metric that we call lambda. Section 2. The Astrobiological Quantum Engine. Welcome to the quantum engine room. And listen, this isn't some far-off science fiction concept. This is running right now on actual 2026 quantum hardware, like IBM's Brisbane processor. What we're looking at is a quantum neural network. It is mind-blowing. This circuit uses just 5 qubits to map the data, and it was trained on 500,000 synthetic atmospheres. Because of how quantum mechanics works, these 5 qubits can explore vast possibilities all at once. It's like instantly seeing every single path in a giant maze. It captures hidden correlations that would literally require millions of parameters on your standard classical computer. Now, what's really fascinating here is how these different quantum tools team up. You've got the variational quantum eigensolver. Just think of it as an algorithm finding the path of ultimate biological harmony. It maps out synergies using real laboratory data from extreme Earth organisms. At the same time, quantum amplitude estimation steps in to provide a massive speed boost, locking in our confidence thresholds. And the absolute best part? This entire quantum pipeline can process a whole planet's worth of data in under 10 minutes. 10 minutes. Which brings us to arguably the boldest claim in the paper. Quantum computing is not just for show here. It's not some buzzword thrown in to grab headlines. Planetary environments are incredibly chaotic. If you change just one element, like, say, the temperature, it wildly alters everything else. It's like a complex web of magnets. You move one, and all the others shift instantly. Because of this deeply chaotic, multiplying nature, a quantum approach is quite literally the only realistic way to process this level of multidimensional data. Section 3. Real-world tests, TRAPPIST and Proxima. All right, let's ground these stunning, hyper-realistic theories in some hard empirical science. The researchers actually put this engine to the test on 2 of humanity's most famous exoplanet candidates. The algorithm isn't guessing here. It ingests an exact 11-dimensional input vector. We're talking real data pulled straight from NASA archives and JWST spectra. It factors in mass, radius, temperature, and a supercritical detail we often kind of ignore, the sheer frequency of daily stellar flares. Take a world like Proxima b. When the LCPV evaluates it, it visualizes some massive, extreme threats. We're looking at a staggering 0.92 risk factor for extreme UV radiation alone. Add a 0.85 risk from tidal locking, which means one side of the planet is just forever scorched by its star, and a 0.80 risk of atmospheric erosion. The quantum engine takes this brutal reality and heavily weighs it against any of the conditions that might have looked, favorable on paper. And here is the final verdict. After collapsing all that massive data through the quantum circuit, TRAPPIST-1e gets a lambda score of negative 2.58. In the LCPB framework, any score below 0 is absolutely definitive. It means the current surface conditions are unfavorable for life as we know it. The metric doesn't sugarcoat it. It's clear, brutal, and totally unambiguous. And this brilliantly illustrates just how sensitive the model is. Proxima b scores a negative 17.0, so it's slightly less negative, suggesting a marginally better environment than TRAPPIST-1e, but it still sits firmly below that 0 threshold. You see, the LCPB index is strictly designed to do one thing: prevent us from chasing false positives. Section 4. The Future of Astrobiology. Now, you might be thinking, well, those negative scores are kind of a letdown. Actually, scratch that. It's a colossal success for the scientific method. It aligns perfectly with our failure to detect water vapor on these planets so far. So, what happens next? The future applications are just thrilling. We're talking about validating this index in situ using Minion nanotech biosensors, which, fun fact, are already proven on the International Space Station. This framework is going to guide target selection for telescopes like Ariel and Plato, and future updates will even let us hunt for life in subsurface oceans. So, the crucial point to take away from all this, brilliantly summarized by the authors themselves, is that we aren't waiting around for the future. We have an astonishing tool right now, today. The LCPB is fully executable, and it creates this unprecedented bridge between cold, calculated quantum mechanics and that deep, visceral human desire we all share to find life beyond our own stellar neighborhood. As we look out into the vast, hyper-realistic beauty of the cosmos, that massive bottleneck of how to process the data is finally solved. The quantum astrobiology engine is fueled, it's running, and it's ready. There is really only one provocative question left for us to answer. Where will we point our telescopes next?